we're gonna go over this book, okay, this chapter, I'm sorry, specifically. And what I want you to see is here in the intro, and I make all these things make sense to me, at least, to me. I put them in there for a reason, okay? DQN, the way I see it, is these guys were sitting around one day and thought, how can we make the problem of reinforcement learning look like a supervised learning problem? Because we have so many different techniques ready to, you want to train a classifier to classify cats. We have that. And, there are theoretical things proven. Everything is beautiful. Everything is shiny. Everything is great. I'm not sure what that means. So for reinforcement learning, the problem is a completely different problem. And I want you to get the intuition as to what is different between reinforcement learning and, I'm going to say, supervised learning. Okay, the one thing, okay, so there are a couple of things there, but let's see. So I'm going to tell you first, more intuitive, and then we're going to go into how they actually, so we can follow the book then and go more precisely as to what is that called. But if you think about how it's done with supervised learning, what you commonly have is a bunch of samples, pictures of little cats. I'm not gonna draw too much, but those are my samples. Those are a bunch of little cats in there, right? And notice something. You have all these pictures in advance, okay? You have the control of the data. So you have the control of the data. You also you know exactly what's a cat and what's not. So the rules of the games are, you're gonna tell your algorithms, remember, we're training a supervised learning model. So you're giving supervision to the model. You're saying that's a cat, that's something else, that's not a cat, and so on. Right? That's one thing. You have control of the data. It's given in advance to you, and you can do anything you want with it. The other thing that is commonly seen in supervised learning is that the data is also diverse. So instead of having so you can imagine a picture of the same cat, and you taking pictures of the same cat all over the place, just going around in circles, taking millions of pictures of your cat, Fifi, right? No, it's not cool. You need data that is diverse, that is independent is the word, but we'll get into the words in just a second. All right, so that's one thing, is that is really, different cats. It's not the same cat. One is red, one is green. That's my depiction of different cats. And that's enough. All right. So this is supervised learning. In reinforcement learning, is you just can't do that. Reinforcement learning is trying to model online learning. You're learning from, this video stream. You can't shuffle me right now. Sorry, it's not going to happen. I come online. The data, the stream of data comes into your sensory things, eyes, ears, and so on, online. So you don't get control of that. You get control of how you learn these data, right? You can record the video, learn later. You can go to bed later and be like, okay, so I kind of understand what he meant and things like that, and kind of replay that in your head. But you don't have control on how the data comes. And also, it's not really that diverse because, what I'm saying right now has a very particular relationship in sequence, right? So I'm saying something, I'm going to flow the whole, teaching in a particular way. You don't get to pick I guess you get to pick if you want to switch videos, right? But other than that, you don't get to pick for this particular stream. So the data in this case, and I like to do it like this, ST plus 1, and this represents states, plus 2, and so on. And then S at time T, which will be the last one. This is reinforcement learning. Reinforcement learning, this guy over here depends on this guy, right? So if you're driving a car and you're turning left, you know that what you're gonna see the next step depends on where you are at this moment, and actually something over here, like a little action, right? In that case will be cap action, right? So that is all, there's a lot of correlation in there. Okay, so that's the main difference. All right, so now we're gonna switch real quick. There are actually words for this, okay? And in the book we have there, this page over here, I actually, so I'm gonna go to the highlights. Basically, you can read this in your own time, but to me the highlight is this. So the data is not independent and identically distributed. That's a reality of online learning, right? When you do a supervised learning, the assumption in the data is independent, meaning that one sample, one cat is not the same cat as the other cat and the other, and so on. There are ways to go around that, but so like the standard supervised learning does not work well if you do it that way. Okay, so independent in that sense, and also identically distributed means that because you receive the data set in advance, you get to shuffle it, right? That's basically what you do every time. You get a data set, you shuffle it, and then you split it, and so on. So it's distributed identically. But in reinforcement learning is not the case. In reinforcement learning, what you do today, so I cannot just teleport all of a sudden and be somewhere around the world. It just doesn't happen that way. Learning online has a distribution that is not identically distributed. Today I'm going to experience something, and a little later I'm going to experience something else, and then later at night, and then tomorrow, and so on. So there is some sequential nature there that is very unique to online learning, and it's very, very cool actually to have that challenge. So I would say those two things, right? So this guy and then this guy. So that would be the first, kind of issue that we're trying to solve. Remember, now let me rewind a little bit. We're trying to see what are the differences between supervised learning and reinforcement learning to try to come up with an algorithm. We're not going to come up with it, but we're going to discover it that way. That basically tries to make the reinforcement learning problem look like supervised learning to the training model. Okay, that's the whole goal that we're trying to get to right now. The second thing is that, and this is a little harder to kind of interpret, but we can go into it, is that, let's see, where, okay, there it is. Is that in supervised learning, and I guess I can use the highlighter, right? Supervised learning, the targets used for training are fixed values on your data set. You have the same data set. You're going to say, this is my training data. This is my validation. This is my test. You grab batches from the shuffle data set, and the data set's not going to change. You keep doing that over and over and over and over and over and over, and then you are going to try to find that optimal, right? Well, in reinforcement learning, that's not the case, right? Because if you think about it, if you want to be like a great soccer player, you start very early, you start, passing the ball and so on, and you are really bad at it. You really do not see things that a professional can see. Okay. So things are changing all the time. Things are, when you are learning, what you are using for learning is changing. Your experiences are going to change every single time step. So we optimize this part. I think is the key here. We optimize the approximate value function, and therefore change the shape of the function. That is possibly the entire value function, which means that the targets change as well. Now, I don't know if you guys are familiar with this, but there is something called as TD versus Monte Carlo. If you don't know very much like what that, I explained in an earlier chapter, so highly recommend you go and check that out, because even though it's kind of like very, how do you say, like basic stuff, or not basic, fundamental stuff. A lot of people, are very, they just want to learn like the state of the art. But if you don't go through that process, then the state of the art, this really doesn't make much sense. But this is true for this guy over here, because there are two ways of, let's see, when it comes a little later, we're going to have the equation, and in there, I might be able to explain the difference between these two. When we get to the equation, if I don't explain the difference between TD and Monte Carlo, let me know, because I think that's important to get the distinction, to understand what it means that this section otherwise may not make much sense. that the targets change as well. What do you mean there? What are you talking about? I think I can help with that when we get to the equations. You can imagine this black line being the value function, having a particular shape. And then so you get the value of the next state to calculate the value of the current state. You use that as an estimate for future, what you're going to get in the future, right? So, but you can see here what I'm trying to say is like the red is really what's going to happen after an update. So all of a sudden, every update, you're changing the shape of your function, right? And then what's going to happen is immediately after you make that update, here is what I'm trying to the point that I'm trying to make is that point, which is the value of the next state, it's already here. It already changed. It's no longer valid. I probably shouldn't say valid because I think that has a mathematical meaning, but I meant it's really not correct. It's no longer accurate. So again, the two problems, the targets that we're using for training are not stationary, the way that supervised learning methods have it. So supervised learning methods, remember, you have the data set, you shuffle it, and then the kind of where you're going is the same thing from the beginning to the end of training. In reinforcement learning, where you're going changes a little bit at a time. As you get better and better and better, there's a new policy. The new policy creates new data. The new data creates new estimates. The new estimates create then a new value function. The new value function creates a new policy, and so on. And that cycle repeats and repeats and repeats. Repeats, and then it's non-stationarity of the targets right there. And the second thing that we talked about, actually, which was the first thing, is that the data is not IID, identically distributed, independent and identically distributed. How do we fix these two problems? So there are actually two techniques. A couple of ways that we can make this better. Reality is online learning is just a different animal, and we shouldn't be trying to make online learning look like supervised learning. That's not a satisfying solution. But for this particular algorithm, it's a good way to. Actually, it was one of the first ones, right? 2013, 2015, two papers, one in 2013, one in 2015, and it actually started a bunch of contributions, right? I mean, can you think it? 2015, is that only 5 years ago? My goodness. So many papers have come after that, and so much like good research is out now, which is is really, really good. All right, so the first thing that we're gonna talk about is so the use of target networks. Okay, the number one addition to DQN is the use of target networks. A target network is just a copy of your network, the same network that you're training, that stays frozen for a couple of steps, so that basically the training of the online network basically uses the frozen values of the target network for many steps before that target network, the weights of that target network actually change again. Okay, so I want to be very clear with that because it's a little confusing. But here the little drawing here may help you kind of understand what I meant. All right, so you can imagine here, this is your target, right? This is in a world without a target network. The approximation would do something like that. So, right, so it's gonna go here, it's gonna go here, it's gonna go here, and so on, right? But the target really doesn't stay there. In supervised learning, it does, but in reinforcement learning, the target actually is jumping because the value function gets better. I think I'm gonna have to. I need to explain the TD and Monte Carlo because otherwise you guys probably don't have a clue what I'm saying. So I realize that. All right. So let's very briefly go. I'm gonna show you the equation. We're gonna go and explain in the whiteboard. And I want people to make sure that they get the differences because it makes sense there. So the equation here for training a network is to use the reward that you experience plus this thing over here, which is basically, oh, look at that, it's fancy. this thing over here, which is basically saying, approximate, give me an estimate of what's going to happen once I arrive to the next state, and pretend that I'm going to take the best action, the action with the maximum value. That takes me to here. So in reinforcement learning, you can imagine a grid world, okay? There's something happening in this grid world. And you always start here. Here's a +1, here's a -1. You want to, let's say that you have a very specific policy. You're always going, or so you have a very specific policy, say like this, right? These are your actions usually. If you're here, you're going to go there. If you're here, you're going to do this, and so on. So that's why I probably need to do more like, streaming more often, because then I could actually, talk about the different problems. And, you think like, what can I do in 1 hour? And I'm like, well, it's kind of hard because I have no idea where people stand to actually help them get into the next level. But we'll give it a try. You want basically to know the value of this state. Let's say that you want to estimate that value. There are multiple ways to estimate this thing. One of them is called Monte Carlo. Monte Carlo is the kind of like more straightforward, like in my head at least. This is the way that I would do it before I knew anything about reinforcement learning. Monte Carlo is drop the agent in there, drop the guy here, and let her run the policy. Let her run it for like 1,000,000 times. It's fine. Just let the agent go around the world, experience all of the things that needs to experience, and then you can average all of that experience. You can average, right? So let's say that the reward here is 0, 0, 0, and so on. Let's say that it's actually 0.1 to make it a little bit more representative of what I'm trying to describe, and so on, right? So maybe there's something like that. You can imagine a world, right? That's Monte Carlo. Monte Carlo again says, let that policy run for a long time, and we're gonna average all of the values, and we're good. We only care about the value of this guy for now. We're good. The other way to do it is what is called TD, temporal difference. And that was, kind of an introduction by Rich Sutton. Well, kind of. That was an algorithm introduced by Rich Sutton. The one thing with TD is the realization that you can experience one step and predict what's going to happen from here on. And then you can immediately update your policy. You don't have to let the policy run all the way until the agent either, gets the +1 or -1. Let's say that these are terminal. Let's say that the agent terminates. So the episode ends once it reaches either this one or this one. Sorry, I guess you cannot see my hand. It's either this one or this one. Okay, that's when the agent ends the episode, right? So it's important to realize that you can also estimate the values of every single step here, this guy, and so on. And then so when you go and transition like this from here to here, you use the estimate from this second state to basically estimate the value of this guy, which is a little weird. It's like saying, okay, well, I made $1 million last year, so I know that for the rest of my life, I'm gonna make $10 million. How do you do that? Like, why would you? It's well, we can do it with days, right? So I make $1 million in a day. I know that tomorrow I'm gonna make so much, and so on. It's a little contradicting or not contradicting. How do I say? Like, it's a little bit. It kind of doesn't make sense when you do it early on, because your guesses are incorrect. That are not right. You have no idea. You're beginning your journey. You have no idea the true value of this guy or the true value of this guy, and so on. So the interesting thing is that in the update equation, I'm talking about that this transition over here, and I probably need to use a different color now. This transition over here actually has a signal that is real, which is a reward. And then you're going to calculate the value of that guy using that reward plus, and probably shouldn't use the discounted value right now, plus the value of that next state, S prime. And when you see Q, that's, basically the same thing, just saying that the value and the action, given that the action is going to be like a max here. But to simplify it, let me just say like that. What I'm saying is you use the value of a next state to calculate the value of the current state. Now, this is not an equation because I need, obviously the whole target, right? But, that's what we're doing there, okay? And then so that's the difference between Monte Carlo and TD. The problem in reinforcement learning, and what I was telling you about the target network, is that when you are approximating stuff, this guy over here is going to be changing every step because this guy over here is related to this guy over here. And that is just going to spiral around like crazy, diverge. And that's why there's so many unhappy people after they try to implement some reinforcement learning algorithms, say like, reinforcement learning doesn't work, this is terrible, I hate it, whatever. Okay. The point is that it's usually, there's some gotchas in there that are not easy to follow. You don't have it in your head until you actually understand the details. And so that's one of them, just to be aware. Okay, let's see. So now we can go back into this. Aha. Now I think you guys are going to understand better this section. What I'm saying here is that because that value function is being trained every step, you can expect this target over here. You can expect that thing that I was drawing in there. You can expect this guy over here to be moving like this. First goes here, then goes here, then he changes here, and then he changes here. And it's just going to keep switching back and forth. So the target is non-stationary. Bad idea. All right. So your training is going to actually try to go towards the target, right? So the training ideally would go here, then get closer and closer and then hit the target. But it's going to go. And then this thing just changed all of a sudden here. And the training just starts flipping back and forth. It's spiraling around, divergence. Oh, okay. End of the world. How do we solve it? All right. So a target network, what it does is to, you have the two networks again, and one is going to be producing those estimates that I talk about. This guy is going to be a target network. Let's put some other color. This guy is going to be a target network. And this guy is going to be training every single time. Okay. So now your target is stationary for so many steps, right? Stationary, boom, changes, okay? And then stationary, boom, changes. And then you go like that, boom, back and forth. Back and forth, hopefully not back and forth, just, a little bit at a time, I meant. This is basically what I'm trying to describe here with the target network. So that's, I want you to grok that just put it in your head. That's the reason why you have a target network. You want the targets to look stationary. I like analogies for teaching these kind of things so that you get it into an intuitive level. Imagine, climbing a mountain, right? And then you say, I want to go to the highest peak. So in reinforcement learning, what you're doing with the target network is putting, stepping stones. Like, okay, I'm going to go to that rock first, then I'm going to go through that path. Then I'm going to go, even if I go down, that's fine. I go a little down, and then I go back here and so on, and then I climb it. You still have the goal that is going up to that, peak all the way in the mountain, right? But what you don't want is to try to go straight to the mountain when you're not going to be able, it's not as easy to go straight to the mountain. In this case, that's basically what we're doing with this target network. We're actually, making the approaching of the true target or the true kind of optimum value a little bit at a time, right? We freeze the network, we solve that problem, then we update the network, we freeze it again, solve that next problem, and so on. Little by little, you accumulate all that goodness in there.